Okay. So let's pick up where we left off last time. And then sometime during today, we'll start bringing stuff together with the mendax platform. All right, so last time we kind of started talking about what is programming, telling a computer what to do. We talked about why is it difficult for us as humans to do this, and we're so good at problem solving that it's difficult for us to break things down into tiny pieces. Um, and maybe some of you saw that going through the mendax exercises, because even though that was a tool that made you not have to focus about syntax and things like that, the fact that you still had to think differently than you typically think on a daily basis, it was still difficult, right, to some extent. So hopefully we're seeing that this isn't something you can just wake up tomorrow and be good at. It takes lots and lots of practice. I broke down how human beings solve problems: memory, asking questions, and repetition. These are our go-to moves. Then we talked about every single programming language having the ability for having facilities for these. So memory is typically done through variables. Asking questions is done through conditionals. Repetition is done through loops and functions, procedures, methods, those kind of things. How are these things represented in mendax? How does mendax let you remember things? How are variables implemented on there? Well, apparently you spent 600 hours on it. You should be very familiar with how to remember stuff in mendax. So who? You can make it a quiz. Should be quiz. Did we have something called a data model in mendax, where you created an entity, right? And then entities had attributes. Is that kind of like variables? Is that saying, okay, I want to have a person, and a person has a first name and a last name and an age? That's remembering stuff, right? All right, and you did all that through their data modeler, where you just created a new entity and drug it down and said, okay, he's got a first name, and a first name had maybe a string type, and a last name has a string type, and an age has a number type, something like that, right? So that's how mendax pulled off memory. And mendax even took it a step further. It said, you can handle memory a couple different ways. We could have memory persist between multiple runs of the application, right? We'll kind of talk about this more later, but they can say, well, you have a database that, kind of like a hard drive that remembers the stuff that you stored through multiple runs of the application. Or you could have non-persistent data, where we're just going to remember for the moment, right? So if I say the number I'm thinking of right now is 5, for the next couple of minutes, you're all going to remember 5, right? But if I ask you week 8, what was that number I mentioned in class? A couple of you might get it right, but in general, that isn't a high importance number. You're going to forget that when class is over, right? Okay, so that would be non-persistent type stuff. What about the concept of asking questions and functions, procedures, kind of the logic side of things? How is that represented in mendax? What was that facility called? All right, so the domain model is kind of the data model thing we talked about already. So that's how we set up things to remember. We only have 3 things in mendax, right? That's how data is associated with each other. I want to know, how do we ask questions? How do we say, if this person is greater than 21, they're allowed to drink? How do we ask those types of things in mendax? Okay, and where are conditions represented in mendax? What's the tool in mendax that we use for conditionals? They're called microflows. Remember those guys? Microflows. So a lot of dragging stuff out there and saying, okay, if this is true, go this direction. If otherwise, go this direction, then do this stuff. So you had this big picture stuff called microflows that allowed you to add logic to your code, right? All right, so if we kind of, let's take this mapping here. And I'll just actually go ahead and let's create a let's call this guy the mendax mapping. All right, so memory is done through the data model or domain model. Okay, so entities with attributes, that's mendax version of that, right? And then we had a couple of pieces to that. We said that data can be persistent or non-persistent. Okay, persistent data is like storing stuff in a database. Non-persistent, so it's available between runs of the application. Non-persistent is just for right now. All right. Asking questions, conditionals, repetition, all of this stuff. So this is, we probably would bunch this all under logic, right? So asking questions, logic, all this stuff in mendax is done through microflows. So that gives us asking questions, that gives us repetition, functions, procedures, those types of things. Because microflows are reusable, right? We can write it once and then attach it to multiple things. Okay. So with that in mind, is it fair to say that mendax is a programming language? Programming language? The syntax is pretty drag and droppy, right? You don't have to write a lot of syntax, but as we see here from what's a programming language, it doesn't say anything about must have crazy sounding words. Doesn't say anything about the syntax. It talks about facilities for doing certain things. Okay? So mendax gives us all of the facilities that the typical programming language would give us. And then it actually gives us some additional stuff. So most programming languages don't have a database built into it. But most applications you might write kind of require persistent data, right? If you have a computer program and you launch it, you use it for 15, 20 minutes, and then you close it, you probably want your data to be stored so that the next time you open it, you can pick up where you left off. Pretty common that you're not starting from scratch every single time you open up a program. All right, so that data needs to be stored somewhere, whether it's stored in a file or some other way. Data needs to persist between runs of the application. Well, most programming languages have inbuilt facilities for file I/O, for writing stuff to a directory, and it might have some tools that allow it to communicate with a third-party database somewhere, but programming languages typically don't have a database embedded within them. So mendax makes your life easier by having that. All right. So that's one piece that mendax brings to the table. Another piece that mendax brings to the table is our interface side of things. So mendax has something called pages, right? Okay, where you can make pages. That's what your screens look like in your app. Well, typically when you first start writing programs, and we're going to see this later today when we start doing some Python stuff, our programs are going to be pretty ugly. Just text-based stuff, prints out hello world, no buttons, all these other things, because we don't have a tool built into traditional programming languages that allow us to build friendly interfaces. That makes sense? So if we were looking at something like Android programming in here or something like that, we would be learning multiple tools. We'd have to learn Java as the programming language. Then we'd have to learn Android Studio with all the drag and drops for buttons and things like that, and then get those guys to talk to each other. So typically, when you think about writing a software application, so if we're writing an application for some business, that application is probably going to store some stuff in a database, all sorts of different stuff, and that's where the data model stuff comes in. And then somebody mentioned the relationships between those things. So that allows us to kind of say, here's all the players in here. So we have this is a class. I think one of the examples in there went through kind of courses, and courses have trainers, that kind of stuff, right? So, this is a scheduled class, CSC535. And this scheduled class for this semester meets at this time in this room. Okay, so we have a classroom, S120. That's an entity, right? We have a classroom entity. This classroom happens to have the name S120. That's its name. And maybe we also keep track of the capacity of the classroom. Maybe how many chairs are in here, how many butts we could have in the seats. Make sense? All right, so that's our classroom entity. So if we take a step back here, let's just do this. So we have a classroom. Shrink this down a little bit. And we decided that classrooms have a name and have a capacity. Those are the things that go into a classroom. All right. Now, we have in this classroom, we have students. Students have a name. Let's just leave it at that. Maybe you have an ID number or something like that, but let's just keep our example simple here. Okay, so students have a name. Now, how many students are in a classroom? More than one. Many students to a single classroom, right? But we're not ready to make that relationship yet, because now we also have a scheduled class. And a scheduled class has a name, and maybe it also has a time, daytime, something like that. All right, so a student enrolls in a scheduled class. So there's one scheduled class. CSC 535 exists one time this semester, correct? Yet there's a whole bunch of you who are registered for this class. So there is a one-to-many relationship between these two entities. Every scheduled class has many students associated with it. All right, now we also have another entity called an instructor. And an instructor has a name. Now, how many instructors are associated with a scheduled class? Just one. All right, so we have a one-to-one relationship between scheduled class and instructor. Let's see, do I have any better tools here? Oh, well, I'll just leave it like that. All right, so one instructor per scheduled class. Then we have lots of students in a scheduled class. How many classrooms are associated with a scheduled class? Just one, right? So we have one classroom associated with a scheduled class. So this scheduled class requires there to be a teacher, one classroom, and then a bunch of students who will attend that class, right? So in the simplest case, this is a data model, right? This is an entity, this is an entity, this is an entity, this is an entity. So something like mendax allows you to create these 4 different entities, assign attributes and types to those 4 different entities, and then quickly associate these entities with each other. What kind of meaning do they have in your application? Now, most of you, because you don't have programming background for most of you, maybe felt that this was somewhat challenging, right? Going through this. I promise you, if you had to create the databases by hand to do this, you would be very happy with how mendax does it for you. All right? Because what you would have had to do is you would have had to create a database table, so you had to write some SQL to generate this table. Then you have to write some SQL to generate this table. You have to write some SQL to generate this table. You have to write some SQL to generate this table. And all that's only going to work once you get a database management system installed. So you got a database management system. Now you have to connect to it. You write your SQL to create these couple of tables. Now, you have to design those tables so that they all relate to each other in a reasonable way. It's called a relational database, right? Okay. Now, once that's done, now you got to go over to your actual software application that you're writing, and you got to get that guy to connect to your database that lives somewhere else. You got to worry about, firewalls and IP addresses and things like that to get those guys hooked up. So there's a whole IT skill set there just to get those two pieces, those two things talking to each other. Make sense?
Yeah.
All right. So Mendix does all that inside of one umbrella. So it's solving a lot of those problems for you so that you don't have to solve those micro problems. Same thing with logic. The micro flows. Yeah, you're at the mercy of what kinds of things you can represent in a micro flow. But when you see later on today, when we start writing this stuff by hand, I think you'll appreciate the stuff that Mendax is doing for you. All right, so Mendax would be considered a power tool. Now, it can go a couple different ways. Well, let me ask you this. So those of you, now that you've all spent some quality time with the Mendax platform, who's the correct end user for something like that? When would Mendax be the appropriate tool for the job?
I mean, the end user for Mendax?
Well, yeah. So when would somebody use Mendax to write a software application as opposed to sitting down and writing an Android app from scratch?
Maybe if they don't have experience with other websites. It's kind of like using Wix to do it.
Okay, so I think that's a good comparison. So obviously, Wix does a lot less, right? You know, Mendax is trying to mimic an entire programming language, where Wix is kind of a glorified, word processor to allow you to drag pictures and stuff in there to make a website that looks kind of pretty, and they give you some templates. But the point is that to build a Wix-based website, you don't even have to know what HTML is, right? It's not an important aspect of it. You need to know that here's a picture and here's some text, and I want this picture to be here and I want this text to be here. And you look at 7 or 8 templates, you say, oh, this is the one I like. And you select it, and now your page looks a lot prettier than you probably would have done on your own, right? Because Wix does all that stuff for you. So Mendax is kind of like that, right? Now, having said that, do you think a professional web developer would ever use Wix? It's a very interesting question. How many of you have done web development stuff before? A couple of you, okay. Are you also familiar with Wix? You kind of know how it works. So as a web developer, would you ever use Wix, or would you view that as being beneath you?
It depends. It just kind of. I guess it kind of depends on maybe who the end customer is, right? Maybe who the end person. Maybe if you have like a relative who's like maybe a lot older, and they just say, hey, you know what? I saw this thing on Wix. I don't know how to use a computer, but I want you to put this website together for me. And maybe you have some more important projects to do. You can just use Wix and just kind of put that together for that person.
Okay.
Maybe for like their business if they don't want to.
So Wix is a power tool.
Yeah, exactly.
Now, in general, don't humans like power tools? And pretty often, power tools are our tool of choice for solving a lot of problems, right? Now, with a power tool sometimes comes some limitations. So Wix is going to have some limitations. You're only going to be able to pull stuff off in terms of the abilities that Wix hands you. Similarly, Mendax is going to have its own limitations, as will traditional programming languages. So any tool we use will have its limitations, and you'll have to solve problems in terms of the abilities that tool has, right? So maybe, well, we're probably going to find limitations on Wix significantly more sooner than we'd find them on something like Mendax. But if most of what you're doing to build a website is all just look, it needs to look good, have links to go to other pages, it's not all that dynamic. Okay, just pretty much a plug and chug, new home page for somebody. Maybe somebody's creating a page for their wedding, something like that. Wix is the perfect tool for the job. Why should somebody who's a web developer use the more advanced tools, but the less power tooly, where they have to do more of the work manually, when they can just slap something together in 20 minutes on Wix? Kind of makes sense? And ultimately, what they'll have in the end is probably something that will look better, certainly will look better quicker than what they would have done manually by using their traditional power tools, right? Now, certainly, when they go to do their traditional web development, they have a lot more options, right? A lot more things available to them that they could do. But if those aren't things they need to take advantage of for a certain project, using a tool like Wix might be better. Okay. Similarly, we look at something like mendax. Shockingly so, and I know we haven't gone, as far in as some of you haven't seen as much of this as others, but mendax actually will connect to third-party APIs. So you can go as far as to make your mendax applications talk to a JSON-based RESTful API and bring crap into it. We'll talk about what that all means. That's a pretty advanced feature. I mean, you're not all that limited with mendax other than learning the tool, right? Learning how to do stuff drag and drop style rather than writing a whole lot of syntax and getting multiple pieces kind of all talking together. Now, having said that, what platforms does mendax target? When you write your application for mendax, where can you use your application? What are your options? So you can view it on the web, right? Mobile applications and tablets. Okay. So it's deploying really to all of our targets, right? If you're on a desktop, you can view it through a web page. If you're on your mobile phone, you can view it as a native application. Tablet as a native application through the mendax app thing, right? But you only have to write it once, correct? And your pages adapt. So you can say, okay, this page, I want it to look this way on desktop and tablet, and I want it to look this way on mobile because it makes more sense. But ultimately, you're writing all your logic one time, and then it's now an app that works on all these different platforms. Well, that seems pretty handy, right? So once you get past the learning curve for the tool, you can produce stuff pretty quickly. Whereas if you were going to do that, let's say you wrote an application to do some sort of classroom type thing like we're looking at here. If you wanted to be on mobile and tablets and web, well, you'd have to create a web version of this using appropriate web technologies, and we'll talk about some of those today. You'd have to maybe write an Android application. Maybe you use do that natively. So you're going to use Android Studio with Java as a programming language. You'd have to create a native iPhone application. So now you're running it, probably using Swift as a programming language, using Xcode as the development environment, and you're going to have to find a Mac somewhere. That's just going to cover iOS and Android. That covers most of mobile, but that's not going to get you on Windows Mobile or BlackBerry or something like that. So you're still limited a little bit, but that still covers most of them. So you have all these disconnected tools that you have to know about and get them all connected together. And you actually might have to write your app 2 or 3 times, right, for those different platforms. Sometimes that's the right tool for the job. Sometimes. We talked last time, just going to go through here, about there being 3 kinds of programming languages. Machine language, zeros and ones, low-level language. We looked at the Hello World for Linux. We saw that one-to-one relationship with the CPU. And high-level languages. Well, we like high-level languages. Now, every now and then, we might have an application that needs to be really, 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 really fast. Would you use mendax to create a video game? Maybe depends on the game. Generally speaking, if we're talking maybe like a trivia game or something like that, maybe. Okay. Are you making Angry Birds with mendax? We're all familiar with Angry Birds. So Angry Birds not a super high, high performance video game, but mendax is not the right tool for that. It doesn't solve that problem. Does that make sense? mendax allows you to make business solutions, or a game like a trivia game or a card game, maybe something like that. It doesn't allow you to have things moving across the screen with animations and stuff like that, at least not at a high level. There's some ways you can pull things like that off, but that's not what that tool does. Okay, so if somebody hires you and says, okay, we're going to make a game like Angry Birds, and you're going to think about all the tools that you know how to use, or all the tools that might be out there that you can take your technology background and apply it and learn how to use those tools, because that's what we've done this last week, right? Everybody in here is familiar with using web, right? We've all used websites and stuff before. We've all used desktop applications. And we've all watched videos. So you had all the tools you needed to go through a pretty verbose tutorial that took you through this whole thing to learn a new tool. Now, after a week, are you all professional mendax developers? No. But do you feel like you know a whole lot more about it today than you did a week ago? If you worked on it for another week, do you think you'd be even better with it? Right? We've been introduced to it. We kind of know a lot about a little, right? A whole bunch of information was shoved into us over this last week. 8-10 hours of video and doing different things. But we're not experts in any of those things. We've done it once, right? It was a monkey see, monkey do. Video said do this, click here, drag this. We did that. But we at least have kind of an understanding of the basics of what that platform is like. We'd have a fighting chance to sit here. We asked the question, could you make Angry Birds with mendax? And we confidently said, no, it's not the right tool for the job, right? Okay, so let's say it's Thanksgiving and we're carving the turkey. What's the right tool for the job? Do we go crank up the chainsaw? Not the right tool. I mean, cool tool to use. Okay, but you're probably not going to carve that turkey with the chainsaw. I mean, it would be fun. Okay, it would definitely be fun. But that's not the right tool for the job. You're going to use some sort of smaller carving knife or something like that. It's the appropriate tool for that job. Now, if you need to cut down a tree, you're probably not going to take that carving knife you used to cut down, carve the turkey. I mean, with enough time, you eventually get that tree down, right? But it's not the right tool for the job. So when you're solving problems as technology experts, we want to identify the tools that are available to us and figure out which of these tools are appropriate for the job we're trying to solve and which ones aren't. mendax allows you to create business-type logic targeting multiple different platforms, web and mobile, in a rapid application development type of system. And it's completely integrated. You don't really have to go outside of the mendax tool to do anything other than maybe connect to third-party data sources. If you want to pull real-time stock quote applications, stock quote information or something like that into your application, well, mendax doesn't maintain stock information. You have to find some third-party tool that will spit out real-time stock quotes, and then you can connect mendax to that and bring that data in. Right? The data comes in like a JSON format, which we'll talk about, and you can tell mendax how to interpret that data. Pretty good. I mean, it's not built into mendax, but they've given you a facility for reaching out and getting that external data. That allows you to solve a lot of interesting problems that you wouldn't have been able to solve otherwise. Okay, but we come up short of writing a video game with it. Make sense? It's just not the tool for that. Okay, so let me go back here. All right, so we talked about functions last time, reusable chunks of code that we write once and call multiple times. So mendax, these are our microflows. All right. We talked about CPUs being the brain of the computer, kind of has a collection of magic tricks. I probably had you last time. Everybody raised their hands and we moved our thumb around, and nobody's impressed that I can do that. Nobody's impressed that I can do that. Nobody's impressed that I can do this. But if I do some of those things in enough motion, then I can do something real. Pick up a soda, drink it, whatever. Those are more impressive things. Now I'm using all these little tiny magic tricks that are available to me, and I'm putting them together in an interesting way to solve a real problem. Make sense? So that's what a CPU ultimately is. It's a collection of seemingly unimpressive magic tricks that we can then call upon in a certain order. And something real happens, something that, from our perspective, for a general purpose computer solves video games, business applications, whatever it is. Okay. We kind of looked at how CPUs are actually built. So in the middle, we have this the processing unit. This is the guy that actually eats those assembly language instructions, the machine code. But then we have some really, really, really fast memory that sits around this guy. And we need that memory sitting there in order for us to do stuff. Now, we've drawn so this is kind of how a computer looks on the inside, right? So we have our processor, we have our system memory, we have our hard drive stuff, we have our I/O devices, and then we have this bus that allows all these guys to talk to each other. Okay? Now, let's draw another picture here. So we have our CPU sitting here on our computer. Now, we're going to operate off of a little bit older computer where we just have a single CPU that's a single core CPU. When I say we have a multi-core CPU, what does that mean? Okay. Interesting. I like that you answered it that way, but it's the wrong answer. What's a multi-core CPU? So this is a single core CPU. This is a dual core CPU, right? Dual core CPU has 2 CPUs in it. Now you said it's faster. Well, it can be. Are 2 processors always going to be able to solve a problem more quickly than one processor? Depends on what? Let's think about this in a real life problem. Okay, we're going to have a race. It's going to be me versus all of you. Okay, but you all get to work on a team, right? Now the problem we're solving, I can solve at speed 10. I'm a little bit quicker than any one of you. You all can solve that problem at speed 9. But you all get to work together. So what do we got here? 6, 7, 8, 9, 10, 11 people. Can 11 people solve a problem at speed 9 faster than one person can solve that problem at speed 10? Why?
I think it depends.
Depends on what?
If they can split the problem.
Depends on the problem. Okay, so I didn't tell you what the problem we were doing was. We're changing a light bulb. I can change a light bulb at speed 10. You, team of 11 people, are going to change a light bulb at speed 9. How many of you is it going to take to change a light bulb? So you're going to pick who gets to go up the ladder, and the rest of you are going to stand there staring at it. While I handily win the speed by doing it at speed 10 instead of speed 9. Make sense? I win that race, even though I'm a single core processor and you're an 11 core processor. Make sense? Now, what if we're shoveling the parking lot here at Concordia? I can shovel at speed 10. Each of you can shovel at speed 9. Who's going to shovel the parking lot more quickly? Easily, you guys, because you can divide that up, right? You can take 1/11 of the parking lot. You can take 1/11 of the parking lot where I'm sitting here fine. I'm shoveling really, really quick, but just a little bit quicker than any one of you. Yet I got to do the whole parking lot myself. Make sense? So multiple processors isn't always better. It isn't always faster, but it does give us the potential to solve certain problems much, much quicker. That kind of makes sense? All right. So in my example here that we're going to originally talk about, I just want to talk about a single core processor. Because the difference between a single core processor and a dual core processor, 2 cores, is that a single core processor can only do one thing at a time, where a dual core processor could technically do 2 things at once. Now, computers are really fast, aren't they? Yeah, we rely on them being fast. So even in our single core processor, can we have multiple applications open at one time? Yeah, as long as the operating system supports that, right? As long as we have a new enough operating system, it knows how have multiple things open at once. But I told you this processor can only do one thing at a time. Yeah, we have 5 or 6 applications open. How does that work? If you're currently typing in Microsoft Word and you have your instant messenger running in the background and somebody instant messages you, do you expect to get that message? Yeah. But your processor can only do one thing at a time. How is that accomplished?
Maybe the process is suspended for some time.
Cool. When do we decide? When do we decide to suspend our instant messenger? I'm sitting here typing away on Microsoft Word. Is it just going to be luck of the draw whether or not it was suspended or not suspended as to whether I get my message? But if he's suspended, he's not going to receive it. But we expect it to be received. And we expect our email to keep updating too in the background. And we expect our Pandora radio to keep playing in the background. We got all these other applications that are running, and we want them all to keep running. We're greedy. People are greedy. We got one processor. We can do one thing at a time. Yet we expect all these different programs to run simultaneously. How is that accomplished in a computer? It can only do one thing at a time. Single core CPU, one thing at a time, period.
It allocates time slice to all these programs.
So if it can only do one thing at a time, but it does it really, really fast, and then switches to a different task, it does that really fast, then switches to a different task, it does that really fast. As long as it's doing all those tasks quick enough, we might not know the difference. Even though it's only doing one thing at a time, if it does enough things, not at the same time, but right next to each other in serial, but it's doing them fast enough, we might be tricked into thinking they're all happening simultaneously. Isn't that the job of a computer? As processors get faster and faster and faster, they can accomplish the same tasks in a shorter period of time. And then we need to look at, okay, well, what are different ways that I can, so when we talk about these on a computer, these tasks that we're referencing are things called processes. All right, so, we might have several processes that are all waiting for the CPU. They're waiting for their time on the CPU. So this guy comes in, he gets his time on the CPU. Maybe he gets 10 cycles on the CPU, whatever that means. Then he goes and gets in the back of the line. Then this guy comes in, he picks up where he last left off, and he gets 10 cycles. He gets to the back of the line over and over and over again. And the hope is that all those things are happening quick enough that we don't notice. We don't care if only one thing is actually happening at the same time because our perception of time is different. How many of you think you could tell the difference between a 1/10 of a second and a 20th of a second? It's too fast, right? Too fast for a person. How many of you can tell the difference between a second and a minute? All of us, right? We can perceive of that time. So if computers can do things quick enough where it switches between things at within an amount of time that we can't perceive, then we're happy. Right? Ignorance is bliss. It doesn't matter that two things didn't actually happen at once. We were happy with one thing happening at once, but happening so quickly that we thought it was happening at once. We're not picky. We don't care how it actually accomplishes it. Many of you drove to school today, right? Did you really care how your engine works? Or the fact that it started and got you here was mostly good enough, right? Some of you might be car people and you say, well, I do care how my engine works. But at the end of the day, you didn't have to care. As long as it ran, burned some fuel, and got you here, you're happy enough. All right, so when this guy is getting his CPU time, and it's now time for him to leave, he's going to go get in the back of the line. The next time through, he needs to be able to pick up where he left off. His data needs to persist. We talked about persistent data earlier, right? He shouldn't have to start from scratch the next time he gets onto the CPU. Because we're just using this arbitrary thing called CPU cycles. Let's just call that a unit of work for your processor. That's all that's important for us in here. if that process takes 100 units of work total to finish, and it's only getting 10, it's going to have to get onto the CPU 10 times in order to actually get complete. Well, if we don't remember where you left off, he's going to keep doing the same 10 instructions each time through. Make sense? So we need to have a way of remembering where they left off. So that gets us into this thing called a PCB. It's a process control block. Okay. This guy, using mendax terms, is an entity. Entity that has several attributes. One attribute is a process ID for this guy. Another attribute is going to be a collection of instructions. So these are that low-level machine, well, this is the machine language that your processor knows how to process. And then it's also going to have a collection of, well, we'll just say collection of register values. So last time we talked about a CPU has some really fast memory location stuff here. We looked at Hello World for Linux and assembly language. We saw that it was loading some values into these 4 locations, right? Now, it doesn't matter which architecture CPU we're working with and how many of these little memory locations there are. The point is that when we leave the CPU, we need to remember all the stuff. We need to remember the current state of the CPU so that we can restore that state the next time we get access to that resource. Make sense? All right, so we're going to have a collection of those register values, all the stuff that the CPU is currently holding in memory for us, so that when we get back onto the CPU, we can copy that stuff back onto the CPU. And when we leave the CPU, we can retrieve the stuff that's on the CPU and store it for next time, so we can pick up where we left off. Then we're also going to need, it's called IP. This is the instruction pointer. That's which instruction are we currently on? Using our example, if we can get through 10 instructions each time we go into the CPU, and it gets a little more complicated than that because there's other reasons we might leave the CPU, but we're not talking about that in our details in here. But if we can get through 10 per trip on the CPU, first time through instruction pointer will be 0, next time through the instruction pointer will be 10, 20, so on and so forth, right? So finally, we're going to finish our program. Great. Now, this is a simplified version of a process control block, but if we think of this entity called the PCB, and this PCB is going to store a bunch of pieces of information, the unique identifier for this process, all the instructions associated with this process, the last known register values so that when it gets the CPU the next time, it can, if it already exists, if the instruction pointer is not currently 0, then it can reload the processor with its previous state and pick up where it left off. And then also we need to know the instruction pointer so we know which is the next instruction we're going to feed the CPU. All right, so that idea of getting onto the CPU and then leaving the CPU is something called context switching. Context switching is expensive. Context switching means that somebody is leaving the CPUs. That means they have to pack all their bags up, remember where they left off, so they'll be able to continue on next time. And then they run to the back of the line. At the same time, the next guy who's getting the CPU is going to unpack his bags onto the CPU so he can pick up where he last left off. Make sense? Well, that's a lot of work. And it gets even worse because I mentioned a few minutes ago that you don't always leave the CPU naturally. We've used this example that we get 10 cycles on the CPU. You kind of mentioned this idea of time slicing or something like that. We're going to say, you get so much time on the CPU before the next guy gets the CPU, so the human being can hopefully be fooled into everything happening at the same time. But sometimes a computer program can no longer use the CPU. Maybe it's at a point where it has to actually leave the CPU on its, because it wants to, because it's waiting for like user input, something like that. If you have a computer program that's waiting for you to enter a number, how long is it going to be till the human being enters a number? Might be a second, might be a week, might be a month, might be never, right? So it needs to leave the CPU and go and wait for that user input to finish before it gets back in line and says, okay, I'm ready for the CPU resource again. Otherwise, you're just going to sit there and just like stare at the wall while it runs out of its number of cycles on the CPU, right? It's 10 nanoseconds, counts down, and then finally it gets kicked off the CPU when it didn't accomplish anything in the last 10 nanoseconds. And if our whole goal is to have the processor constantly busy so that we're faked out and we think multiple things are happening at the same time, we don't want to have a whole lot of wasted time on the CPU, right? The guy's not able to take advantage of that resource, he shouldn't be riding. Make sense? All right, so this idea is called context switching, and context switching is expensive. So we want to minimize the amount of time we do that. This is an operating system idea. So why are we talking about it in here in a programming class? Ultimately, when we write software, all of these things play into decisions that we might make. We have to understand how things are actually working under the hood, how our computers actually function, so that decisions that we make will translate into a program that runs well. Make sense? And also knowing why a program maybe isn't doing what we thought it should be doing. All right, so we'll swing back into this stuff in a little bit. So last time we talked about digital stuff, zeros and ones. All right. Now, we mentioned that computers are digital, on and off. So when we think about the kind of language, the kind of numbers that computers like, think about numbers. Computers, they like binary, right? Zeros and ones. Binary is a fancy name for base 2 number system. Now, what about humans? What kind of numbers do we like? We like decimal. Decimal, that's the base 10 number system. Why do we like base 10 number system? Is it just because when we were kids, somebody decided that's how we count and we just went with it? Above our pay grade? So generations ago, they just decided, oh, that's how we count. Why do you think we like base 10? Ten fingers, right? If we only had 8 fingers, we'd like base 8. That's, when you're a kid, you learn how to count that way, right? Okay, so humans like base 10. Now, we have a couple of, let's call it number systems that computers also like. And there's a good reason for it. We'll see that reason probably, we'll see it today probably. We won't have a deep understanding for it, but this is other given information that's important that we understand. There's 2 other bases that are commonly used by computers. Anybody know what bases other than base 2 computers often use? Base who? You gotta actually say it out loud. You're allowed to be wrong. It's okay. You said base what?
8.
Base 8. Yes. Okay, so that's called octal. So we have base 8 number system. Okay, what other one? Hex. So we have the hexadecimal. This is base 16 number system. Okay, and we'll explain in a little bit why computers also like those. And it really has less to do about computers liking them. It really has more to do with how humans interface with the computers. Those 2 guys have kind of a convenient little compatibility with the way computers work under the hood. Octal and hex allow us to do some stuff and quickly get it into binary, which ultimately the computer likes. Okay, and we'll see this. But we like base 10. So at the end of the day, if human beings are working with the numbers, we want to be working with base 10. Just like last time we talked about that if human beings are writing the code, we want to use a high-level language. That language that has a one-to-many relationship with the CPU. We write a couple lines of code, it turns into hundreds of lines of code on the CPU. It's a power tool. We like that. Well, we want to work with base 10 if we're doing mathy stuff. Unfortunately, computers like base 2. Once again, we're at odds. We're not speaking the same language as the computer. We can't even agree upon numbers. All right? So, what if we need to get the decimal version of a binary number? What's your favorite binary number? What are the legal bits? The most understandable way of saying it is the legal digits in a binary number, but they're actually called bits. What are the characters that make up all binary numbers? Just zeros and ones. That's the entire alphabet we have to work with when we write a binary number. So 10110. Is that a binary number? Okay. Could that be a decimal number? Yeah, we're allowed to use zeros and ones in decimal. Well, that's 10,110. So somebody's going to have to tell you what the base is. So when I say that's base 2, that's binary, you'll look and say, yeah, that's a legal binary number because it only uses the alphabet of 0 and 1. That is 0 to the base minus 1. What are the legal digits in base 10? 0 to 9. So all of our numbers that we write, we represent them using all the digits between 0 and 9. What about octal, base 8? What's the alphabet for octal? Don't operate off your memory, operate off of the base. Octal is base what? Here, I'll let you, she can cheat off of her. Octal is base 8. What's the legal octets for base 8?
Alphabet A.
Who?
Alphabet A.
Alphabet A. That's a made up. A couple minutes ago, I said the legal alphabet for any base is 0 to the base minus 1. The base is 8. 0 to 7. 0 to 7 illegal octets. Okay. What about hexadecimal? And now you can answer. All right. Okay. Hexadecimal, base 16. Well, we might say right off the bat, well, that's 0 to 15. Well, 15, 14, 13, those aren't single characters. That's not a single alpha thing. So we need representations for the 2-digit values. So hexadecimal supports 0 to 9, and then A through F. Okay. What about base 37? We don't have a name for it, but does base 37 exist? What are the legal digits in base? What are the legal? What's the alphabet for base 37? Huh? I want you to apply the knowledge that I've taught you in the last 3 minutes. If octal, no, you got to do the math. 37 would give you how many letters in the alphabet? Because 0 through 9 is the first 10. Then 26 gives you 36. Base 37 is 0 to 36, right? All right, so if decimal is 0 to 9, binary is 0 to 1, because base 2, it's 0 to 2 minus 1, which is, if octal is 0 to 7, what's base 37? 0 to 36. So the legal alphabet would be 0 to 9, and then A through Z. Make sense? Then we've run out of alphabets. Okay. Now this has to do more with This is the Roman system where we have our numbers, and then the English alphabet. So then you can say, well, how can we represent values that are even bigger than base 37? Well, you need a bigger alphabet, right? You could maybe tack on another alphabet. So maybe base 38 goes 0 to 9, then A through Z, and then maybe you switch over to the Klingon alphabet. And you get the first character of that. You know how many characters in the Klingon alphabet?
Yeah, not really that much into Star Trek.
Everybody know, you've heard of Klingons before? You've heard of the show Star Trek? You've never heard of Star Trek?
No,
No, come on, dude.
I don't like that.
No, I don't care if you like it. You're telling me you never have heard of a television show called Star Trek.
Never ever.
Never heard of it.
Yeah.
I don't believe that.
That's all.
Have you ever watched like any television show or they reference that on TV and radio and stuff all the time? Everybody else in here has heard of Star Trek, correct?
Yeah,
You may never have seen it,
ask Gaia.
but you've heard of it,
Ask-
right?
Yeah, I don't watch any.
I didn't care if you watch it.
I
You've heard of it.
no, I
Okay,
didn't.
I've never seen a Martian, but I've heard of Martians. I don't even know if they're real.
If I ask you about something, it might touch it with you. Did you have any idea about
It depends on what it is. Star Trek, yeah. Star Trek is ubiquitous. You've heard of Michael Jordan, right?
I heard of that.
Yeah. Well, he's from our culture.
But I don't have to.
Star Trek would be like Michael Jordan. Man, that's shocking to me. No, it's shocking.
Like that.
Well, do a Facebook
Maybe
poll.
you wanna show Spock or something.
Huh?
Maybe if you show Spock, you'll be able to recognize it.
Oh, you think Spock might like trigger it?
I mean, like, 'cause that's a very popular.
Yeah, it could be.
Maybe.
This guy?
This guy, this is the first time. I haven't seen him before. I swear to you, I haven't seen him.
Man,
before.
that's like that fact is amazing to me. I mean, I know plenty of people who've never watched Star Trek, but just references. People reference, man, that's amazing to me. In any case, in the show Star Trek, which is a very old show, now they started making movies. So like there's the new version of Star Trek, they make movies. There is an alien race known as the Klingons, and they have a language. And if you look it up online, somebody has actually created the Klingon language. And it only has 22 characters in it. So that doesn't help us. So using English is going to be better. So you would need an alphabet that has more characters.
I have a question. I think, I'm not sure if I can remember where I saw this. In terms of representing a certain base, you can actually go from A to Z, but then you can actually do like A, B, and then.
Really, you would have to set that up ahead of time that's how you want to represent it.
Oh, okay.
Because what we're going to see here in the next little bit is the way we convert numbers is the pattern is identical. We just have to agree upon how do we represent a 10? How do we represent 11? How do we represent a 53? Make sense?
Right.
So if you have set up the rules for that and you want to say a 53 is PP or something like that, that's fine. But somewhere that has to be documented so that whoever's moving it to a different base can work backwards and they know what that code means. That makes sense? In actuality, though, AA probably wouldn't really be compatible because the whole reason we represented 10 with an A is because we wanted a single character for it. Yeah, so really we would need to represent a 52 with a single symbol. Maybe it's a smiley face. Something like that, or maybe a kanji character from kanji is Japanese, right? I think so. Yeah, I think kanji characters, their Japanese letter system, they have like the weird pictures and stuff like that. Or take Arabic or something like that. Well, characters that are different than, the English language. Individual characters, and we can have those represent some values. Okay, so let's look at converting from binary to decimal. So I've told you that this value is a base 2 number. Okay? That's a base 2 number. We want to convert that number to base 10 because we like base 10. So how do we do that? I'm going to actually write this a little differently. 101, 110. Is that the number I had, or is it pretty close? So I have an extra one here? All right. So there's my binary number. That's my base 2 number. This is the 1's place, the 2's place, the 4's place, the 8's place, the 16's place. Now, how did we get those values? We can write this a different way. This is the 2 to the 0th place, 2 to the 1st, 2 to the 2nd, 2 to the 3rd, 2 to the 4th. Make sense? Because we're dealing with base 2, this guy is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. If we were dealing with base 8, this would be 8 to the 0, 8 to the 1, 8 to the 2, 8 to the 3, 8 to the 4. So any number to the 0th power is 1. So this is always the 1's place over here. And as we're walking to the left, we multiply it by the base. So this is the 1's place times 2 is the 2's place, times 2 is the 4's place, times 2 is the 8's place, times 2 is the 16's place. Make sense? So the way we convert this base into decimal, so base 2 into decimal, we take this value, the 0, multiply it by the place. So it's 0 times 1. We add to that this value, 1 times the place, 1 times 2. We add to that this value times the place, 1 times 4. We add to it this value times the place, 0 times 8. We add to it this value times the place, 1 times 16. So that is 0 plus 2 plus 4 plus 0 plus 16, which is 22. 16 plus 4 is 20, plus 2 is 22. Okay, so this binary number is the decimal number 22. Make sense? To convert from any base to decimal, you follow that exact same pattern. So let's steal this. Create another slide. Octal to decimal. So octal numbers are made up of, what's the alphabet for octal numbers? 0 to what? 0 to 7. The base minus 1. All right. So we're going to pick our favorite octal numbers. This is going to be a 2. This is going to be a 6. This is going to be a 5. We'll leave that as a 1, and we'll put a 9. Oh, you were listening. All right, 9's not legal, right? We need to be 0 through 7, so we'll put a 4 there. All right. This is the 8 to the 0's place. This is the 8 to the 1's place. This is the 8 to the 2's place. 8 to the 3's place. 8 to the 4's place. That is, this is the 1's place. This is the 8's place. This is the 64's place. This is, what is that, 256? 64 times 8. Nope, 512. Times 8 is what, 4096? Yep, 4096. It's the 4096 place. So to do the math, we take this value times the place, so this is 4 times 1, plus 1 times 8, plus 5 times 64, plus 6 times 512, plus 2 times 4096. Go ahead and copy that, paste it here. So that's 11,596. So this octal number, 26514, is equal to 11,596 in decimal. Make sense? So we see the pattern. We use the same pattern both times. Okay, so let's have you do one. So we're going to change this. It's going to be 1, 1, 0, 1, 1. So go ahead and take a couple minutes, convert 11011 from binary to decimal. I'm going to pause the recording. Somebody remind me to unpause it once we resume. All right, we got it?
Yeah.
So tell me, what's the answers? What are some of the answers we got? 37? 27? Anybody got a different answer than that? So everybody got 27. Oh, good. So let's do the math for that. This is 1 times 1 plus 1 times 2 plus 0 times 4 plus 1 times 8 plus 1 times 16. That's 27. All right, so everybody's good with that? Just as another practice, let's pick a new octal number. We'll make this 1, 1, 2, 6, 1. So convert the octal number 11261 from base 8 to base 10. Take a couple minutes to do that. What do we get for this one? 4785. Okay. Everybody agree with that? All right, so this is 1 times 1 plus 6 times 8 plus 2 times 64 plus 1 times 512 plus 1 times 4096. $4785. All right. So we feel like we're getting pretty good at that pattern, converting from some base into base 10. Okay. So now take a couple minutes. I want you to convert the decimal number 11,261 into the decimal number to its decimal equivalent, showing your work. And we're going to have somebody come up here and show the work on the board. Decimal to decimal. I promise you, your answer should be 11,261. I want you to show me how you got to that. We're converting from base 10 to base 10, showing your work. Make sense what I'm asking? Remember, when you converted from base 2 to base 10, use the same pattern as when you converted from base 8 to base 10. Why shouldn't the exact same pattern work for base 10 to base 10? All right, so let's look at this. Let's draw our boxes in here. All right, this is the ones place, right? Which place is this? This is the ones place. What's this place? Tens place. What place is this? Hundreds place. What place is this? Thousands place. What place is this? 10,000th place. So this is 1 times 1 plus 6 times 10 plus 2 times 100 plus 1 times 1,000 plus 1 times 10,000. 11,261, 11,261. See how that works? All right, so we're feeling pretty confident with converting any base, let's say any base from 10 and below, since we haven't looked at the letters yet, into base 10. Okay. Go ahead, close your notes, close your laptop, take out a piece of paper. Quiz time. Notes and laptop closed. You can use your phone or whatever as a calculator, but I want you to show your work. If you need to use your laptop as a calculator, that's okay, but don't Google this. I want you to see all your work. All right, and this is an individual exercise, no teams. Okay, so make sure you have your name on the paper. We're going to convert 12788 from base 9 to base 10. 12788 from base 9 to base 10. Okay, so let's solve this guy. I'll go ahead and steal this guy for it. All right, so this is 12788. This is the ones place, the nines place, the 81s place, 81 times 9, 729s place. And times 9 is 6561's place. 6561. Okay. So this is going to be 1 times 8. I'm sorry, I'll just write it in the right order like I've been doing. 8 times 1 plus 8 times 9 plus 7 times 81 plus 2 times 729 plus 1 times 6561. Make sure I didn't have that extra stuff there at the beginning. So 8,666. All right, so correct answer is 8,666. All right, questions about that? All right, let's take about a 15-minute break. We'll come back and then we'll start talking about converting to like things like hexadecimal, things like that.